Chapter 15, Quantum Translation. Section 15.7, the UV-Vis spectra of conjugated polyenes. We can estimate the HOMO-LUMO gap for polyenes, for example 135 hexatriene, assuming the conjugated pi electrons are free particles along the one-dimensional carbon chain. This is the structure of 135 hexatriene. Triene means we have 3 double bonds, and 135 specify the position of the double bonds, carbon 1, carbon 3, and carbon 5. And this is a simpler structure for 135 hexatriene. Now it does look like a one-dimensional box for the pi electrons. Alright, now let's look at the MO of this molecule. Let's focus on the pi-type MOs, molecular orbitals. There are 6 of them because we have 6 carbon atoms. Each carbon contributes 1 p electron in 1 p orbital. So we can use 6 p orbitals to make 6 MOs. Those are all pi-type MOs. The bottom 3 are occupied. The top 3 are unoccupied. The reason is we have 6 p electrons. The 6 p electrons only occupy 3 MOs, the bottom 3. Now, how do we know which MO has higher energy, which MO has lower energy by looking at this? Well, it's very simple. If you look at the bottom MO, you can see gray, 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 gray on top. They're all gray, bottom all white. So there's no node separating those p orbitals, 0 nodes. Now let's look at this side 2 MO. There's 1 node in the middle. Okay, we can cut it. Assuming gray is positive, white is negative. So between plus and minus, there's a 0 in the middle. Now this MO, plus, minus, plus. Between plus and minus, there's a 0. Between minus and plus, there's another 0. We have 2 nodes. Here we have 3 nodes. 1, 2, 3. 4 nodes. 1, 2, 3, 4. 5 nodes. 1, 2, 3, 4, 5. So from bottom to top, we have 0, 1, 2, 3, 4, 5 nodes. And the energy increases as the number of nodes increases. The bottom 3 are occupied by the 6 pi electrons. The top 3 MOs are occupied. The bottom 3 with fewer nodes are bonding orbitals. The top 3 are anti-bonding orbitals. And again, we analyze the number of nodes. We analyze the now quantum numbers for those MOs. If we assume this is just a one-dimensional particle, of course with a zigzag shape, but still it's considered as a one-dimensional box. And we can see, well, if we remember, in a one-dimensional box, the particle may have quantum numbers from 1, 2, 3, 4, 5, 6, etc. So for the particle in the box problem, the bottom MO corresponds to n equals 1. The quantum number is 1. Quantum number 2. Quantum number 3. For the HOMO, n equals 3. For the LUMO, n equals 4. So we have the quantum number of HOMO equals 3. The quantum number for the LUMO is 4, assuming this is a particle in the box problem. Now we'll just estimate the HOMO-LUMO gap for 135 hexatriene, assuming that 6 electrons are free particles along the carbon chain. We need to determine the length of the one-dimensional box. The 135 hexatriene carbon chain consists of 3 double bonds, 1, 2, 3, and 2 single bonds. The typical single bond distance is 1.5, and the typical double bond distance is 1.3. So we're going to just estimate the average 1.4. We have 5 carbon-carbon bonds, so the total length of this carbon chain is roughly 7 angstroms. Okay, this is a rough estimate. A is equal to 7 angstroms, and we know the energy levels should be n squared h squared over 8ma squared. So for HOMO, we need to use 3 squared multiplied by this. For LUMO, it's 4 squared multiplied by h squared over 8ma squared. Now, what's the HOMO-LUMO gap? It's the difference between 4 squared and 3 squared multiplied by h squared over 8ma squared. So really, it's just 16 minus 9 times the Planck constant squared over 8 over the mass of an electron over the length of the one-dimensional box, which is approximately 7 angstroms. Plugging all these numbers on the Wolfram alpha page, you get 8.6 times 10 to the power of negative 19 joules. That's the HOMO-LUMO gap. We can now calculate the wavelength of the photon that can promote an electron from HOMO to LUMO. The photon energy has to be this, the energy difference between HOMO and LUMO. So we set up the equation Hc over lambda equals the HOMO-LUMO gap. Solve this equation. Lambda is 230 nanometers. And this is how we predict the HOMO-LUMO gap for a polyene. And also, we can predict the UV-Vis spectra for a polyene molecule.